Jianxin from Intel. His experience covers various layers of interconnection software stack, including kernel and also user space libraries and middleware. So I'm excited to welcome here today to OFA. His current focus is in the GPU accelerator scale out with RDMA devices, and hence the talk focused on that topic. So Jianxin, welcome, and let's see if we can hear you.
Thanks, Divya. So my name is Jianxin Xiong. So today's topic is about progress of upstream GPU RDMA support. This is a follow-up of the presentation I made last year on the OFA workshop about the GPU RDMA support using the DMA-BUF. Next slide, please. So here's the outline of today's talk. I will start with a brief overview of a GPU RDMA, how it works. And then I'm going to give an overview of the prototype I presented last year on the workshop. Then followed by the status update of the work. So about the progress we have made so far and the major changes to the design and to the code. And then finally, we'll give some thoughts on the potential future works. Next slide, please. Okay, GPU RDMA, here I refers to the scenario. So we want to do the RDMA operations directly using the GPU memory. So nowadays, GPU has been used widely in computations for HPC workload and the AI workloads. In many situations, this computation will involve more than one node. So those nodes are usually connected with high-speed interconnection, like InfiniBand. Those NIC has the capability to do RDMA operations. That means the data flow going directly from the memory to the NIC and then to the remote NIC and then to the memory again. So if we look at this picture here, the red box shows the data flow of the RDMA operation here for the GPU RDMA. What we see here is the data flow starting from the GPU memory, and the NIC will read the data from the GPU memory and send it to the remote NIC, and then put it directly to the remote GPU memory. So this is one scenario. It's also possible the remote side is not the GPU, it probably is just system memory. So RDMA operation has been supported by NIC for a long time. Usually the system memory is used for this kind of operation. What the NIC does, it has a way to get the memory physical address from the operating system and store that inside the NIC into a table. That when doing this RDMA operation, it can do the DMA operation directly from the system memory without the involvement of the operating system itself. However, when GPU memory is used in this scenario, it's a little bit more complicated. The things that the GPU memory usually is in a separate space. I mean, this is not directly accessible from the not directly known by the NIC. So the NIC needs to find a way to get the information about the GPU memory in order to program its internal table so it can do the DMA transaction. This is usually done through the memory registration phase. So we look at the left side of the picture. The red path is the memory registration path. The application gives the virtual address to the NIC driver. the NIC driver trying to translate that address into DMA address, so to program the NIC. For GPU memory, so the NIC cannot do that directly because the system, the regular operating system call, like get user pages, cannot do that for the GPU memory. So here, the NIC driver need to talk to the GPU driver in some way to get the address information, so it can program the NIC. Also, at the higher level, the RDMA application will need to some out-of-band mechanism, or maybe in-band mechanism to exchange the RDMA keys. So the remotely they know where to find the target memory. Next slide, please. So one key issue about doing the GPU RDMA is the RDMA driver need to talk to the GPU driver to get the virtual to physical address translation. Last year, we presented a prototype that used the DMA-BUF as the mechanism to do this address translation. Here's the picture shows how the entire stack works. So basically, the application will allocate the memory using the API provided the GPU library. The GPU library will talk to the GPU driver through a specific device using I/O control. GPU driver allocated the memory and then exported the memory as a DMA-BUF object. After that, it can then get a file descriptor for that DMA-BUF and pass that around back to the application. The application then use the file descriptor to various layers of the libraries, for example, OFI or IBverbs, and this file descriptor had to be passed around to these layers, finally down into the RDMA driver. The RDMA driver then can import the DMA-BUF object using the file descriptor, and then call the specific method defined by the DMA-BUF to get the address translation to program the NIC. And the NIC can do the peer-to-peer DMA operation over PCIe Express, and then perform the RDMA operation in the end. Next slide, please. Over 1 year's work, this software architecture has been involved a little bit. So we look at the red part. Those are the major changes so far. At one side, the device interface, we moved from the card interface to this render interface that is more suitable for regular user. The card interface is more like directly for the GPU, user space, the rendering and the privilege the operations. And then the application, can optionally get this some information, the file descriptor and the base address of the memory allocation at different phases, depending on the user layer API it is using. For example, if application is using the verbs library directly, it needs to call the GPU library to get the file descriptor and the base address of the DMA-BUF and pass those information to the verbs API directly. However, if application is using OFI, it just need to pass the proper interface value and the device value to the OFI API. And OFI internally will call the GPU library to get the file descriptor and the base address in order to calculate the needed parameter to pass to the RDMA library. And also the RDMA library API and the kernel space API has changed a little bit compared with last year. Finally, there is additional callback mechanism from the DMA-BUF to the RDMA driver that can handle the situation that the DMA-BUF itself can be relocated by the GPU driver at any time. So next slide, please. Here's a summary of the current status. So the good news is the latest patch set has been merged into upstream. This includes both the kernel space and the user space patches. The kernel space patch is included in the kernel 5.12. I checked a few days ago, the RC3 has been released. The user space patch is included in the RDMA core 34. So they should work together because the new API added to the code. So to get to this status involves a long round of code review and rework, redesign. So basically, the kernel space patch, we have 16 versions. Starting from the first version, we submitted in the mid-April last year, and the last version, the version 16, is around the mid of December. Finally, it got merged into the Linux RDMA system in January, and merged into the Linux mainline in February 22nd. The user space patch set also evolved from the first version to the 7th version. It started a little bit later because, I mean, usually you only got the kernel patch to a certain stage before you actually submit the user space patches. But anyhow, it evolved from the version 1 in basically sometime in the November, and finally the version 7 in the end of January, and it got merged into RDMA core in January 26th. Next slide, please. So here are the major changes compared with the last year's prototype and today's the latest code. So basically, one change is that we moved from using the write interface to the IO control interface for this user space API. Secondly, we reworked the user space API to make it simpler and somewhat, yeah, the parameter is more reasonable to how to reflecting how DMA-BUF is used. And the DMA-BUF usage, we moved from the static attachment to dynamic attachment. As a result, we no longer require the DMA-BUF to be pinged. So we allow the DMA-BUF to be moved by the GPU driver. And there's one additional requirement with the new implementation is the NIC has to support on-demand paging. In the end, we also added the PYVERBS support and the unit test to the RDMA core. The full change history is available in the submitted changes set in the cover letter. So here there are links below in these slides. Next slide, please. So here we'll talk a little bit of detail about each individual changes. The user space verbs library communicate with the kernel space through a special device, the uverbs device. Traditionally, this is going through the write method. So however, at some point, there was a change of the direction. So all the new commands needed to go to the I/O control interface. Our prototype was using the right interface, so that was not acceptable. So we moved the entire thing to the I/O control interface. The change is a lot. I mean, the mechanism of how the I/O control interface is used and how this is organized is very different from the right interface, and not because of the system is different, but because how the RDMA core implement those, they are using very different basic mechanism. So this is a big change, but I mean this is necessary to get into upstream. Next slide, please. And the user space API is greatly simplified. Now we have only one new API for memory registration for the DMA-BUF based memory region. So compared with the regular memory registration, the API has some different things. One is the parameter. So instead of passing a virtual address to the API, we need to pass an offset. This offset is relative to the beginning of the DMA-BUF object. So even though the memory allocated has from the GPU buffer also may have a virtual address, but usually that virtual address could, I mean, you don't know this information about. I mean, what we really need to know by the kernel is the offset from the beginning of the DMA-BUF. So by passing this directly there, so the verbs library don't need to call the GPU library to do the calculation. And then the other change is there's a new parameter IOVA that allows the user space to pass some kind of the virtual address to the kernel. So in the future, when doing RDMA operation, that address is going to be used instead of using the offset. That is mostly making it more user-friendly. For example, you allocate a buffer from the GPU library, and that virtual address can be used for this IOVA. So this RDMA operation is going to be used in a similar way as the regular memory, instead of using the zero-based fashion. The other parameter is the file descriptor of the DMA-BUF. I mean, yeah, that is necessary to for this new interface. And the user space library that provided by GPU side for the memory allocation should provide the method to find the DMA-BUF file descriptor and also query the offset of a virtual address within the associated DMA-BUF object. Next slide, please. So the big change is we move from the static attachment to the dynamic attachment. The DMA-BUF, originally DMA-BUF supported static attachment only. So by doing this, when do the attachment, the buffer is pinned into the place and cannot be moved. However, the most GPU driver, I mean, I have to say, I mean, almost all the upstream GPU drivers, they don't allow pinning device memory. So what exactly happened with the static attachment is the driver will move the buffer to the system memory. So when you do a static attachment, so that's not what we want for the RDMA. So we want the direct DMA from the device memory. So at some point last year, The dynamic attachment, was enhanced with some new functionality. So by providing additional operations to the from the importer, so that with that support, the dynamic attachment allows the buffer to be not append. The importer will provide a callback function. This is called whenever the buffer moves to a different place. So inside the callback function, the importer should invalidate address mapping in the NIC that is related to the buffer. So to support this, basically the NIC has to have some functionality like a on-demand paging support. So basically, it has to handle the situation, the internal the entries for that memory region could be invalidated. So this is the preferred way for RDMA usage, and this change happens at some time between our first version of the patch and the third version of the patch. So that's how we did that change. In the middle, and not before we submitted the first patch set. Okay, next slide, please. So here's a workflow in how we did that inside the kernel space to handle the dynamic attached DMA-BUF. So in the middle is a set of help functions we implemented in the RDMA core, the core driver. At first, there's a umemory DMA-BUF get. That is the function to import the DMA-BUF object using a file descriptor. So inside of this, it will call the dynamic attach function. And also, the callback function will be passed there as a parameter. And then there's another function to map the DMA-BUF pages. By calling this function, it actually get all the address translation currently exist for the current location of the DMA-BUF. And this can change at any time, but when the changes, a callback will be called to update that. And there's another utility function for unmapping these pages and to release DMA-BUF, and there's the general umemory release function. We'll call that one to handle the situation specifically for DMA-BUF. The right-hand side is the related DMA-BUF operations defined by the DMA-BUF API. And the left side of the picture is the actual flow coming from the user space. The user space memory registration call will finally land into the vendor-specific RDMA driver. There's a driver method called the register user memory region DMA-BUF. And that one implemented by every vendor driver that's actually supporting the registration of the DMA-BUF based memory region. So after calling the function, the memory DMA-BUF get function to import the DMA-BUF, it will also call the page for the handler to do the initial paging for all the pages. So that to optimize. So in most cases, when the RDMA operation starts, the page is already there. So the information is already there, so can do the DMA directly instead of paging the page one by one. So this is the performance optimization. The vendor driver also needed to define this invalidation callback. So both these, so when the invalidation callback is called, it will call the DMA-BUF RMAP pages to free the reference to the DMA-BUF pages, so the DMA-BUF can go ahead and then move the pages. And at the same time, it will invalidate the page translation table inside the NIC. And the NIC will pause or any of this incoming or outgoing RDMA operations using that specific memory region. So yeah, next slide, please. So the last changes is to the user space RDMA core. So there's the PYVERBS is defined in the user space RDMA core as an interface using Python to the verbs API. So that is allows very fast experimenting with the verbs API. Instead of writing a program to test, you can just write a Python script. You can do the RDMA test. So all the verbs API functions are required to have PyVerbs support, and also required to have unit test written in the Python scripts. So we added the support for the PyVerbs. So this including a set of utility functions that allocate the DMA-BUF object using the DRM IO control interface, and a new Python class DMA-BUF that wraps around the DMA-BUF allocation, and a new class DMA-BUF MR as the object representing the memory region. And also we updated the infrastructure so it can build a module with mixed Python and a C source. For the unit test, we defined the new test class to test the memory registration functionality, and also the test class to test the RC traffic using the DMA-BUF based MR. So basically, with RDMA core, the unit test that we can test if this newly added DMA-BUF based MR can function not properly on the system is being built or being tested. Next slide, please. We also made some changes to the LIBFABRIC implementation. So for the API side, it has been exist for a long time. The mechanism to handle the device memory, basically the FI MR reach ATTR, that function can be used to register memory region with actual parameters specific for device memory. So one of the two parameters is the I-phase, the interface, that distinguish between memory allocated from the device using different API. For example, it could be from CUDA or from Rocker or from ZE. ZE is a level 0 API from Intel that is going to work for the Intel GPU. For the ZE API, the internal mechanism is the DMA-BUF for this RDMA support. So it has a few functions to get the DMA-BUF file descriptor and also get the base address of that memory allocation, so we can calculate the offset as the parameter to pass to the new memory registration API for the IBverbs. Those device memory support is provider dependent, and there are a few mechanisms to tell the application if the provider actually support this mechanism. So there's a pull request to the LIBFABRIC. This has been merged as for today. So this adds support to the verbs provider. As now the verbs provider can properly handle the memory allocated by the Z interface and the passing down to the new RDMA core library and work properly on the new kernel of kernel 5.12. Next slide, please. So here's some thought on the future work. So right now, the support for the DMA-BUF is somewhat limited from both sides. From the GPU side, DMA-BUF itself is widely supported by most of the upstream GPU drivers. However, the supporting the dynamic attaching is limited to only some of the GPU drivers. Many of the other drivers are just doing the moving the memory to the system memory, moving about the system memory. Only a few GPU drivers can actually support this peer-to-peer style operation. And also there are some GPU drivers that they don't even support the mapping operations. So they only support from the renders doing the mapping to the CPU for the CPU access, but not the peer device mapping the DMA-BUF. So for those GPU drivers, we needed more support from the community to actually enable more GPU drivers to have the full support for the DMA-BUF based peer-to-peer access mechanism. And for the NIC side, right now the implementation requires on-demand paging capabilities. But this is also only limited to the part of the NICs. Many of the NICs on the market are actually does not support on-demand paging. There's a two front we could possibly get this relaxed. One, if it's possible to relax the GPU buffer pinning restrictions. So for some GPU, it may be possible, to relax this restriction, so allow part of the memory be declared in advance. So this are pinnable, so can be pinned for a certain amount of time for the RDMA operations. If that's to be the case, and then the restriction on the NIC side can be relaxed. The other side is the on-demand paging is somewhat overkill for the mechanism required for the dynamic attachment. What really needed is the way to pause the RDMA operations when the MR is invalidated. We don't really need the page level faulting mechanism. But that is also, we don't know if any NIC has this kind of a reduced level of the paging support, or if that is actually any benefit to implementing this way. So there's a lot of discussion needed, and we'll continue working with the entire community to see how it's going to evolve. And also in the software ecosystem side, we still have a lot of work to do to enable the new API in the application and the middleware side. That's concluded my talk.
Thank you. There is one question here. Is it correct to assume that when callbacks occur to notify of buffer movement, that the actual movement hasn't happened yet, so that in-flight read-writes to those pages return consistent data until the invalidations can be done?
Yes, that's right. I mean, that's
Okay.
actually the purpose of the callback. So the callback is to ensure when the final buffer is moved, everybody using that has already cleared up.
Okay, thank you. Any other questions? Dwayne, does that answer your question? I just want to make sure. Otherwise, please feel free to pipe up. Okay, cool. Yeah, that's good.